Hey guys, welcome to our first video for polynomial functions. So polynomial functions are really cool. With polynomials, you can actually take all that we've done for linear functions and quadratics and just stick it inside polynomials because a polynomial function takes all of those into account. So let's just, real quick, let's throw out that definition, right? So all of our definition of functions are going to be pretty similar. For the most part, they're all going to say, so in this case, a polynomial function is any function that can be written as, so for polynomials, the first one I'm going to write out here is going to look really weird and messy. Something on my sleeve? Oh, looks like I got some baby spit up on there. Good times. So a polynomial is, what I'm going to write up here is going to be a very generic form, and it's going to look really messy and weird. We'll talk through it, and we're going to write down an example of one and hopefully make it a little clearer what's going on. Okay, so let's talk about this. So a polynomial function is any function that can be written like this. So f of x equals, so these are little subscripts. So they're like an exponent. They're written small and above, or in this case below. But what these represent is they represent just kind of a way to kind of keep count. Okay, and so if we kind of look back to what we're doing here, we can kind of think of going up. You have a 0, a 1, 2, 3, 4, 5, 6, all the way up to whatever number n is. Okay, so this a sub n is one thing, and that is just a number, it's a constant. So it could be like 5 or negative 13 or 12.4. It's just a number. Okay, so we have a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot dot dot. So we continue that pattern all the way down to a sub 1 times x plus a sub 0. So there's a couple requirements here. First, the one that I wrote on here is a sub n does not equal 0. Okay, if a sub n were to equal 0, then this wouldn't be our a sub n because that would be 0. So then we just say that this is a sub n instead of a sub n minus 1. So basically, if you say, oh, that's 0, well then be like, cool, well then that isn't a part of it, and this is where we start. The other thing is that n is a natural number. Okay, so natural numbers are like a good counting number. So there's 0, 1, 2, 3, 4, 5. Okay, so n has to be a natural number. And if I take a natural number and subtract 1 or 2 or 3 as we go, we're always going to have a natural number. So we're always going to have a positive whole number exponent going on here. Okay, so we're always going to have something like 5, 7, 18, 2, 0 could be one. But we'll never have something like negative 4 or 3 halves or anything like that. So our exponents on our variables will always be positive whole numbers or natural numbers. Okay. So this is a very basic definition of a polynomial. So it's kind of confusing because we've got like all these a's and stuff like that. So I want to break this down a little bit and do a couple little examples to kind of show you four different functions, kind of show you ones that is and are not polynomials. we had pause the video, write these down. All right, good job. Now, let's talk about these. So if we look at each one of these, okay, there's 4 different functions. 3 of them are polynomials, 1 of them is not, okay? And the way we can identify it, I mean, it might be kind of easy for some of you. You might be like, oh, look, I see it right there. That's awesome. You may have caught it when you're writing them down. So let's talk about them. If we look at this one here, this matches our kind of form that we had, that a sub n, x to the n, and so forth. Now, one thing I want to note is a sub n, x to the n, that does not mean that these numbers have to be the same or anything like that. This is just saying that this number here is the coefficient, or the number that's multiplying by our variable. So coefficient is a term that you're going to want to make sure you're comfortable with. This is the coefficient of the x to the 5th term. So this would be our a sub 5. So for function f of x, if I were to say what is a sub 5, you would say 7. Because 7 is the coefficient of the x to the 5th term. Okay, and as we move our way down, we have 7x to the 5th plus 8x to the 4th plus 12x cubed. Oh, that's good, right? Minus x squared. Well, we have a minus. The definitions and everything was plus, right? But we know if we add a negative, that's just subtraction. So that just means, since this is the x squared term, that means that a2 is negative 1. That's not bad. Minus 2.1x. Ooh, we talked about natural numbers, right? We said like every... But again, this is the coefficient. Coefficients can be anything. There's no restriction on those, okay? So negative 2.1, perfectly fine. So negative 2.1x plus 5. Perfect. That right there is absolutely a great polynomial function, okay? Moving on to g of x. Negative 29x to the 15th minus 12x to the 4th plus 3. Now, we may look at this one and go like, it is, right? But what about all of the other ones? Right? Where'd those all go? We said that they couldn't be, the coefficients couldn't be 0, right? But what we said was that a sub n could not be 0. In other words, this first coefficient can't be 0. We didn't say anything about any of the other ones. All of the other coefficients, they can be 0, okay? And since those can all be 0, or any number of them can be 0, any polynomial doesn't have to have every single term. So we don't have to have x to the 15th, x to the 14th, 13th, 12th, and all the way down to x to the 0. We can simply have whatever ones are relevant or have a non-zero coefficient. Okay? So since this doesn't break any rules, and by that we mean that all of our exponents are positive whole numbers, we're good. H of x. Oh, yeah, h of x. We look at this, read it, we have 5x to the 9th, fine, minus 4x to the 4th thirds. That right there is our problem. Because of that, this is not a polynomial function. Polynomial functions cannot have exponents that are not positive whole numbers. Okay? Now this last one. This is kind of a weird gray area. This comes into the idea that natural numbers contain 0. Some people say it does, some people say it doesn't. It's a really weird, fuzzy area of mathematics. But we're going to say it does include 0. So this right here is a polynomial. This is like 5 times x to the 0. And so this is a polynomial, in fact. It's a really boring one. We don't really deal with it. All of the things that we're going to talk about, we're just basically kind of go like, man, this doesn't exist. We're just going to ignore it because it's boring. It's just a constant horizontal line. It doesn't have all the fun features that a polynomial has. So there's a way to kind of recognize, is something a polynomial, is it not a polynomial? The biggest key is the exponents. If any of the exponents are anything other than positive whole numbers, it's not a polynomial. Okay? All right. Now, I want to talk about the 2 different forms of a polynomial function. Now, if you think back, real deep back in your brain with linear functions, right? We talked about them in slope-intercept form, y equals mx plus b, or f of x equals mx plus b. In the past, you've probably heard of the slope-intercept form, maybe point-slope form, where you have something like y minus y1 equals m times x minus x1, that sort of thing, right? And there's some other formats for linear functions that you can have as well. For quadratics, we had 3 forms, right? They were, list them off for me. That's right. Standard, factored, vertex. Any order doesn't matter. Polynomial only has two. Okay? Polynomial has the standard form, which is the definition that we had originally, a sub n, x to the n, a sub n minus 1, x to the n minus 1, a sub 1x, plus a sub 0. So, that's our standard form, right? It's that whole multiplied out thing. If we're in the other form and we want to get to standard form, we just need to multiply it out completely. Okay? To do the other form, it's similar to a quadratic. Can I help you?
Yeah, can you make me math with me?
I am busy working, baby girl. You want to say hi?
Hi.
All right.
Daddy, who is it?
Say hi.
Hi.
Okay. Now, go.
Oh, Daddy.
I'll play with you after lunch. Sorry about that.
Daddy,
So,
who are you talking to?
my students. Okay, you gotta go. Sorry about that.
Why?
The other form that I have that we have to use is the factored form. Okay. One sec. Okay, the factored form. So the factored form, very similar to that of a quadratic, looks like a sub n times x minus r1, x minus r sub 2, dot to dot, all the way up to x minus r sub n. Now, we have a lot more factors than a quadratic does because this exponent here could be a lot higher than a quadratic, which would just be 2, right? Which quadratic, remember, ax squared plus bx plus c, polynomial. Notice we have this a sub n out here, just like we did with the standard form, just like on a quadratic. That's also similar, okay? We get similar things based off of these functions. Now we get a little more information based on these two things that we're going to talk about in just a minute. That's specific to polynomials in general. But just like in a quadratic from standard form, we identify the y-intercept, which is helpful but not really helpful with the polynomial too much. But in factored form, we get all of our x-intercepts, our roots, our zeros. So what's really cool is that this means that this function has roots x equals r1, r2, r3, up to rn. Now you may be like, that's not that cool, but the cool thing is, you remember what a root is. A root is an x-intercept, okay? So what that means is that a polynomial, let me swap down for this one. Polynomial can have n possible roots. Or in other words, there can be n different x-intercepts or roots or zeros of a polynomial. So that's why a polynomial can kind of bounce up and down and go kind of crazy. Now, this doesn't mean there are, there's just possible n roots. Okay? So, these are our two forms, standard and factored. 90% of the time in this class, we are going to be dealing with factored form because it's just far easier to work with. But I want to talk about standard form and some of the pieces from that. Now, I'm going to leave these up here because I want to talk about adding on a little bit. Polynomials are a very vast set of functions. And one of the ways we classify them is by what we call their degree. So the degree is simply the highest power of x in standard form, or it is the number of factors in factored form. Notice both times that is n. So the degree of polynomial is n. The degree of a polynomial is n. To find that in standard form, you are going to simply look through that equation, that function, and identify the highest exponent on x. Okay? In standard form, you're looking for the highest exponent. Now, they'll try and trick you, right? And this is something that I'll do on some of the homeworks just to kind of test your knowledge. I'm not always going to put these in what we call descending order, where we have the highest power first. I'm going to mix these up. Because it's addition, we can mix them around, it doesn't matter. 3 plus 5 is the same as 5 plus 3. So I could write this as a sub n minus 5 plus a sub n minus 6 plus a sub n plus a sub n minus 1 minus 2 minus 3 and go through there. Okay? So I can mix these around. Now in factored form, and we're going to see this a little more in the example videos when we're really diving into kind of dealing with factored form, you're going to kind of see kind of two versions. And one is kind of the fully written out thing where you have every single r value written out. But what's cool with polynomials is sometimes those r values are repeated. You can have something like x minus 2, x minus 2. In other words, the root of 2 happens twice. In which case, we don't really write x minus 2, x minus 2, x minus 2, however many times. We would use exponents. And so you might see something like x minus 2 squared. Okay? And so because of that, when we're looking at factored form, to identify the degree, we're looking at factored form, we're trying to identify the degree. If it's in fully factored form, if none of these factors have an exponent, we simply count how many factors there are. If they have exponents on them, you can still count, just kind of saying if this is squared, you would count that twice. Okay. The other thing you can do is add all of the exponents of the factors. Okay. So in factored form, we add the exponents of the factors. In standard form, we find the highest power of x. Okay. That is how we find our degree. All right. So that's how we find the degree. I want to talk about that now because I have those both written up. All right. Now what I want to talk about is I want to just list off real quick the 4 things you need to have to graph a polynomial. To be able to graph any polynomial, you need 4 things. You need to know the degree, which that is n. The other thing you need to know is the leading coefficient. The leading coefficient, if we're looking at standard form, okay, the leading coefficient is simply the coefficient of our x to the nth term. It's our a sub n value. And if you remember, when we had the factored form, a sub n was also out in front there. So our leading coefficient is a sub n. Pretty easy. Okay. Now we need 2 more things to be able to graph a polynomial. Okay. And this is sketching the graph. We're not getting like an exact, precise graph drawn. We need to know the roots, right, which are also referred to as zeros, or x-intercepts. Okay, we need to know the roots, zeros, or x-intercepts, and we need to know the multiplicity of each of those roots, zeros, or x-intercepts. I'm just going to say roots from now on. Okay, so we need to know these 4 things. The degree, which is simply n. The leading coefficient, which is a sub n. We need to know the roots, their zeros, and their x-intercepts, which all the same thing. And we need to know the multiplicity of each of those roots, 0, x-intercepts. Okay, each of those roots. These 2 things combine to tell us something, and these 2 things combine to tell us something. They each tell us a different aspect of this polynomial. And so those are going to be really helpful when we're working with these functions and trying to graph them. Now, if you remember about trying to solve inequalities, one of the ways we had to do it was that big table, but another way we talked about when we had quadratics a little bit, It's really easy if we can get a graph. If we can get a graph, we can just read off the graph. Okay? So that's how we're going to solve most of our problems with polynomials, is by graphing. So these 4 things are really important to be able to know how to do, and graphing is really important to know how to do. We're going to have a video specifically for graphing polynomials on that next. So, I want to talk about the degree and leading coefficient. The degree was our n value. Right? Now, n had to be a positive whole number. Positive whole numbers, they split very easily into even and odd. So our n is either going to be even or odd. That's always how we're going to consider it. The next thing we need to know is our leading coefficient, which can be anything, right, except 0. So if it can be any number except 0, that leads us to the natural split of positive and negative. And so using those splits, even and odd, positive and negative, we get 4 different possible combinations. And so what I'm going to do here is we're going to talk about what's called the end behavior, because that is what these tell us. So the degree and leading coefficient tell us the end behavior. Okay? What that means is it tells us what's happening to our function as x is going to positive and negative infinity. Okay? So what we're going to do is we're going to create a little chart, and you'll see a blank kind of 4 graph thing in your note sheet, in your lecture guide. And that's what we're going to fill in here. We're going to fill in all this end behavior. Know this table. Okay, this is something that you need to know. You need to have it. It's not something that you want to have on the test on a note sheet so you can look it up, right? Maybe have it so you can verify if you're uncomfortable with it. But if you know it, you'll be that much faster. And I know some of you are now completely not paying attention because I said the word test, right? Don't forget your test is coming up in a couple weeks. I will be posting more information about that about a week prior to when that test is going to open. And you guys will have plenty of time, don't worry. So, I'm just going to split this into fourths. Now remember, our degree was n. So, we can have that our degree is even. And that's going to be this left-hand side. Or our degree could be odd. Okay, that's going to be our right-hand side. Now, the other thing was our leading coefficient. That could either be positive or negative. So, say a sub n, because a sub n is our leading coefficient. So, a sub n could be positive, so greater than 0. And that's going to be on the top. And then a sub n being less than 0, that's in our denominator. Okay? Now in each one of these squares, I'm going to have a little graph and then we're going to have some information written here as well. Okay? So what's really cool with polynomials is, notice, all I said is n is even and the leading coefficient is positive. I didn't say what n is. N could be 100, n could be 1 billion, or n could be 2. A sub n, our leading coefficient, could be 1, or it could be 100,984. Okay? It doesn't matter how big these numbers are. All that matters is, are they even and positive? If they are even and positive, we fall into here. So what's cool about that is we can think of the simplest polynomial that has an even degree and a positive leading coefficient. What about x squared? Leading coefficient is 1, degree is 2. 1 is positive, 2 is even, that's it. The graph of x squared looks like this. Goes up, right? So our end behavior looks like that. Now, we don't know what's happening in this middle section. That middle section is defined by our zeros and their multiplicities, and that's what we're going to talk about in a little bit. Okay? So, the way we state this, the kind of formal mathematical statement of this end behavior, we say that as x goes to infinity, f of x goes to infinity. And then we also say that as x goes to negative infinity, f of x goes to infinity. And what this is simply referring to is if we look at our graph, as x is going to infinity, so as we're moving out this way, our function is going up. So as x goes to infinity, our function is going to positive infinity. And as x goes to negative infinity, our function is going to positive infinity. Nice and easy. Now let's jump down to this next one here. So this one here, a nice easy example, is simply negative x squared, which that is just a reflection. So that means our hand behavior does this, but again, we don't know what's happening there. There's the end behavior for that. Even degree, negative leading coefficient. Now, we're going to write this part very similarly. Now, what's really nice is, for all of these, it's going to start the same. As x goes to infinity, f of x goes to. And as x goes to negative infinity, f of x goes to. What's going to change for all of these is this last symbol. And it's either going to be a positive or negative infinity, depending on what situation you're in. So, we're going to write these out. Ooh. As x goes to infinity, f of x goes to, so as x is getting bigger and bigger, as x is going to infinity, this function is decreasing. So this function is going to negative infinity. And as x goes to negative infinity, f of x goes to, so as x is going to negative infinity, our function is going down, it's decreasing. So f of x goes to negative infinity. And there's the end behavior for this. Good, you can read it. So, there's those two. Pause if you need to write these down. I'm going to step in front of them. And I'm pretty big, so I'm not going to block them. So, now what if n is odd and our leading coefficient is positive? Now, we can think of x or n equal 1, but that's boring because it's a linear function. So we're just going to think of f of x equals x cubed. Now, for those of you who are unfamiliar with x cubed, looks like this. Yeah. Like that. So, the end behavior looks like that. And just like we did over here, as x goes to infinity, f of x goes to, as x goes to negative infinity, f of x goes to. So if you look at this, as x goes to infinity, so as we're going out to positive infinity, our function is going up, which means f of x goes to infinity. And as x goes to negative infinity, our function is going down, so our function goes to negative infinity. Now, hopefully you can figure out what's happening here. The only difference between this one here and this one here is that our leading coefficient is negative. So we're just going to hit this x cubed with a negative 1, which is just a vertical reflection. So our example function so our sample function is f of x equals negative x cubed, which takes this and just flips it over, which means this part goes up now and this part goes down. So now when we're creating our statement, as x goes to infinity, f of x goes to, so as x is going to the positive direction, our function is going down. So here we're actually going to go to negative infinity. And as x goes to negative infinity, f of x goes to, right? So as x is moving back this way, function is going up. So f(x) is going up to positive infinity. So there is that nice completed chart. This is a really nice, it's very informative. There's a lot of pieces of information going on here, a lot of good stuff. We don't do this a whole lot. I will use this for some questions because it's easier to frame this than both of the tails go up or both of the tails go down, or the left tail goes up and the right tail goes down. We can make this statement and talk about the end behavior a lot simpler. However, it's not something we're going to write a whole lot. I'm not going to do a whole lot of questions, say, write the end behavior. I'm just going to say graph the function. And you're going to have to graph the end behavior in there correctly. So I kind of get away from this. But it is a good idea to know how to do this, know what this means, right? Kind of understand how those symbols translate to a sentence. So if you don't have this written down, pause, write this all down, get this down in your notes. Good. All right. Now, as far as the zeros go, I'm not going to dive into finding those because if you have, the only time we're going to find them is factored form. There's no quadratic formula type thing for anything other than quadratic that we're going to ever use. There is one for a third degree polynomial. I think there's one for a fourth degree polynomial that is conditional. It works sometimes, not all the times. The third degree polynomial one, that formula is large enough that if I wrote really small, it would fill up this whole board easy. The fourth degree polynomial, that formula is big. It's so big that it would probably fill up like 6 of these forms if I wrote really tight. I'm talking like fill in every little bit of space. So those are not anything that we ever use. When we're finding zeros or roots of a polynomial, it's because we're given it in factored form, or it's something very easily factorable. And so what I mean by that is, let's look at okay, let me think real quick before I mess this up. Okay, so let's say this is our polynomial. I say, what are the zeros here? Well, it's not in factored form, but what we can really easily do is we can see that in all of these, there is an x. Matter of fact, there's x squared. So we can factor out an x squared. And what's more, we can actually see that there's 3, -3, -6. So I see that there's a 3 in all of it, so I can pull out a 3 as well. So when I factor that 3 out, when I pull that 3 out, that 3x squared, I can then look at kind of each of these terms and fill in what's left. And so when I do that, I can think about this very easily. I can either think of what's 3x to the 4th divided by 3x squared. Well, the 3's cancel. X to the 4th divided by x squared leaves me with x squared. Another way to think of it is, okay, 3x squared times what gives me -3x cubed? Well, that's easy. That's just -x. Okay, so whichever way of those works best for you, that's what I want you to do. Okay, take -6x squared, divide by 3x squared, -6 and -3 become -2, x squareds cancel out. So I get this. This is a quadratic. This can be factored. Now, if you're one of the people that never factor when we're doing quadratics and just always jump to the quadratic formula, I would recommend going back and practicing some factoring, looking at how to factor those. Watch that video again and thinking about this. So we need to find two numbers that multiply together to be -2, yet add to be -1. That's easy. -2 and +1. -2 times +1 gives me -2. -2 plus 1 gives me -1. Good to go. So we took this polynomial and we factored it. Now real quick. What's the degree and leading coefficient? Pause the video, figure it out. Alright, welcome back. Good job figuring it out. Awesome. Now, I'm just going to write down what you already know because you already know it, right? You already did it. The degree in our standard form here is simply the highest power of x. Well, this is x to the 4th, x cubed, x squared. Highest power is 4. Bam. Degree is 4. Now let's look down at factored form. How do I get 4? I have two factors here, right? It's 1, 2. But we also have this x squared here. Now another way we could write this is like that, because x minus 0 is just x. And if we wanted to kind of write this in that fully factored form, okay, we'd write out x minus 0 twice because it was squared. Now from here we can see we have 1, 2, 3, 4 factors. Bam, we're done. Here we go, okay, well I have 1, 2 here, and then I have 2 of them here, so that's 2 and 2, it's 4. Another way to think about it is if we have factored form, we can kind of add the exponents on the x terms. So here this x term has an exponent of 2. This x term has an exponent that isn't there, which means it's a 1. So if there's ever not an exponent, it's an exponent of 1. And this has an exponent of 1 as well. So we get 2 plus 1 gives us 4. Okay. Now a quick note on fully factored form. If I have something like this as one of my factors, is not in fully factored form. Fully factored form has to be where all the factors have to be x plus or minus a number. Okay, it cannot be 5 minus x, and it can't be any coefficients in front of that. It has to be just x plus or minus a number. So if you get a problem on the homework that asks for things like that and you're getting it wrong, you're like, what's going on? Check to make sure that those factors are actually factored out all the way. Okay. Now, leading coefficient. This is really easy. In standard form, it's simply the coefficient of our highest powered x term, 3. In factor form, it's simply the term out front. Boom. There we go. We got degree and leading coefficient. Good job, guys. You rock. I love you. You're awesome. Okay. Now, I want to focus in on a similar example. Right here. Now, you may be like, well, the only thing we did is we just cubed that plus 1, and that's right. First of all, what did that change? Did it change the degree, the leading coefficient, or both? Pause and think. That's right. It just changed the degree, right? The leading coefficient is still 3, but now we added in, essentially we added 2 more factors of x plus 1, because at first we had x plus 1. Now we have x plus 1, x plus 1, x plus 1. So we added 2 more factors, which means our degree went up by 2. So, looking at this, we have different roots and different multiplicities. The way I like to keep this organized when I'm writing this out, when I'm doing a problem, we're going to talk about this again when we do our example graphing these, okay, is I like to use a little table system. Where I have my roots written on one side and their corresponding multiplicities on the other. Now, the roots here are pretty easy to identify, okay? They're simply asking, for this, for roots, we're simply asking what values of x make this equal 0. Well, from these two, it's really easy, right? Because we have this times this times this. So I have a number times a number times a number, right? Once we put an x in, we simplify. For that to equal 0, one of those three things has to be 0. So that means either x minus 2 is 0, x plus 1 cubed is 0, or 3x squared is 0. So for x minus 2 to equal 0, what does x have to be? Right? 2, because 2 minus 2 is 0. So we get a root at 2. For x plus 1 cubed to equal 0, well, the cube doesn't matter, right? Because I can't cube a number and make it become 0 unless that number was already 0. So I really just have to ask myself, x plus 1, what makes that equal 0? And that's just negative 1. And lastly, we have 3x squared. Now, this is something that is really kind of, I see a lot of students trip up on this issue, okay? Because I'm looking at this, because there's an x, if there wasn't an x, if this was just like 3 out here, okay, we wouldn't get anything, because 5, let's say x is 50, and let's write this down. Okay. what does this equal if x is 13? Well, it's 5. What does this equal if x is like negative 23? It's just 5, right? You think of it like this. If I have a piece of chalk in this hand, and I grab my eraser over here, how many pieces of chalk do I have? I still just have 1, right? I didn't do anything with this. That's what happened here. But if I add in that x, right, like we have in here, now, what does this equal if x equals 0? 5 times 0 is 0. So when we're looking at this leading coefficient and this kind of factored form, we need to see, is there an x there by itself or with that leading coefficient? If there is, we have a root at 0. If there is not, if this isn't there, if we just have 3 times x minus 2 times x plus 1 cubed, then there is no root at 0. We would just have roots of 2 and negative 1. So make sure you're careful checking if there is an x there or not. So there's how we find our roots. It's that easy, right? We didn't write anything down to find those. We just looked and thought. Now for the multiplicities, that's really easy. Okay, I'm going to write this down over here. Multiplicity is the number of times a factor is repeated. So the multiplicity of a zero, of a root, of an x-intercept, is simply the number of times that factor is repeated. So if we look here, we're like, well, none of these are repeated, right? But if we were to write this all the way out, we saw that in that kind of worked out example at the end, right? We had that x minus 0, x minus 0. Since this is squared, this would occur twice. Since this is only to the first power, this is only going to occur once. Since this is to the third power, this is going to occur 3 times. So that means our root at 2, it came from this factor here, which only happens once, so it has a multiplicity of 1. Our root at negative 1, that came from this factor here, which that factor occurs 3 times. So our root at negative 1 has a multiplicity of 3. And lastly, our root at 0 came from this factor here. That factor is squared, so that occurs twice. So it means our root at 0 has a multiplicity of 2. That is how we kind of go through and identify that. So the 4 things you need to graph a polynomial are the degree and the leading coefficient, because those 2 things tell you the end behavior. The next thing you need is the roots and their multiplicities, because this is going to tell you what happens between the end behavior in that kind of dotted bubble. And I'm going to talk about how this tells you that in just a sec. Okay? So, I'm going to create this general chart for the multiplicity of a root and then the behavior of that function. What's really cool about this is because of the way polynomials work, as our x values get closer and closer to that x-intercept, that factor kind of dominates the scenario of what's going on. So in other words, if we look up here, as we get closer and closer to 2, if we think about like on a number line, as our x values get closer and closer to 2 from either direction, this factor is what dominates everything else. It's what dominates what's happening. Okay, and I'll do a little Desmos video kind of demonstrating this as well. So you can feel free to watch that if you want some kind of more visual of what's happening there. So with that factor determines what our graph does there. And there's 3 possibilities. Our possibilities is that the multiplicity is 1, that it's even, or it's odd and greater than 1. Now if our multiplicity is 1, our function, as we come to that 0, that x-intercept, that root, our function behaves like a linear function, like a first degree polynomial. In other words, so if these are Imagine if you will, these are two just random chunks of the x-axis. They're separate. If our function is coming from above, what's going to happen at that root, if that's our root there, is our function is going to pass through in a linear fashion. In other words, the function isn't going to like flatten or bounce off or do anything crazy. It's just going to kind of continue on its path and go right through. Now, if we're coming from below, then obviously we would do that. So if a multiplicity of our root is 1, when we're graphing it, this is how we're going to graph it. Now, if it's even, right, think back to an even degreed polynomial, very simple, x squared. What does x squared do at 0? It touches and bounces off. And that's exactly what any 0 root with an even multiplicity will do. Okay? It's going to come down, touch at that root, and bounce off. Or it's going to similarly come up, touch that root, and bounce off. Okay? It doesn't matter if it's squared like this, or if I were to say write this one as 100,000. Okay? It is going to touch at that root and bounce off. That's what it does. Now if it's odd greater than 1, it looks like x cubed. Now if you know the graph of x cubed, if you don't know the graph of x cubed, grab your graphing calculator right now, go to the y equals, type x cubed, look at zoom standard, and graph it. Okay? Look at the graph of x cubed. If you can't figure that out, go to Desmos, look at x cubed. It comes up, flattens out at the 0, the origin, and then goes back up. Same thing happens here. Okay, we get this kind of flattening out thing that's happening, right? All these tick marks, by the way, those are just the roots. So those are just kind of showing where the roots are. So it kind of comes up, flattens a little bit, goes through the x-axis, and passes up. Goes down, flattens out a little bit, goes through the x-axis, and goes down. That's it. Those are the 4 things you need. The leading coefficient and degree tell you the end behavior. The multiplicity tells you what the function does at the roots. And then the roots tells you where it does what it does. Those are the 4 things you need. If you know those 4 things, you can sketch a graph of any polynomial. It's that easy. It's so awesome and so fun. That's it for this video. You guys go crush it. Look out for a couple more example videos.